So let's look at a couple more limit problems that are a little bit more sophisticated. Limits involving, what do we look at? What kind of limits we've been looking at, guys?
Logarithms.
Indeterminate forms.
Indeterminate forms and ones that involve logarithms. You're right, Katie.
Okay.
Okay, so let's see if this one turns out to be an indeterminate form first. So let's think about plugging it in. So if we approach 1, and how do I read this? Approaching 1
On the right.
from the right-hand side, so we should be thinking about like what kind of numbers?
Positive.
What is a number that approaches 1 from the right-hand side? Like 1.0001 or something like that, right? Those are the kind of numbers you should have in mind when you're doing a right-handed limit like this one. Okay, so if I put numbers really close to 1, but a little bit bigger than 1, into the natural logarithm, what would that look like? Remember, natural logarithm looks like this. There's 1. So approaching 1 from the right-hand side on that, I'm getting really close to what?
0.
Approaching 0 from the right-hand side, I'd be getting close to negative infinity. Approaching 1 from the right-hand side, I'm getting really, really close to 0, right? The y-coordinate's going really close to 0. So this is really basically, if we plug it in, kind of like 1 over 0, which is undefined, but remember, it's really, really close to 0, so it's more kind of like something like that, right? Or 0.00001. What's 1 divided by, in other words, something really small, really big? This is infinity. So this limit is equal to infinity for that term, and if you put 1.0000001 right here, and you subtract 1, what do you have left?
Negative.
You're going to have 1 over something really small again, which again is going to be infinity, and in between them we have a minus. Infinity minus infinity? Unknown. Indeterminate. So, where do I go from there? Well, how did we do this yesterday? We had the log way to do things to help out. Caleb. And we also had, that was using logarithms. But we also, before that, we just tried to change it into something that's a more comfortable indeterminate form, like 0 over 0, or infinity over infinity. And we had to do that in the logarithm process as well, right? So how do I do this one? So it's infinity minus infinity. Great. What is a way I could change this into another, more comfortable indeterminate form? Any ideas? We've got 2 fractions. What's a reflex? Common denominator. Now, it might not work, but see, you have reflexes for a reason. Let's see if our reflex worked. It's called intuition. So, making this a common denominator, what are we going to have? You guys do it for me. What's the common denominator? Yeah, it's weird.
ln x times other stuff.
Other stuff? Maybe I should put the other stuff in front to make it clear, right?
Yeah, other stuff.
Like the other stuff.
Times
ln x. So what's this one missing? Natural
log.
log. What's this one missing? X minus 1. So I'm going to have an x minus 1 right there. Times 1 is x minus 1, right?
Minus the natural log of x.
Natural log, minus the natural log of x. Just use black. There we go. Okay. So now let's see what happens when we plug it in. So when we plug in 1 now, we're going to get, basically 0 minus, we just talked about what happens to this. I guess I shouldn't have erased my shape up there, but that gets closer and closer to 0, right? So this is going to go to 0 on top. Are we comfortable with that? Because that's 0 and you put 1 there. And we talked about the graph and how it approaches that x-intercept, which is 0. If you put 1 here, you're going to get 0 times 0, which is 0. Now what can we do? L'Hopital, exactly. So this is going to be equal to the limit as x approaches 1 from the right, due to L'Hopital's rule being allowable because of 0 over 0. And if we L'Hopital the top, what are we going to get? minus 1 over x, right? And on the bottom, what are we going to have to do to take the derivative of the bottom? Distribute. You could distribute, that's smart, but even if we distribute, isn't part of that going to be a product rule? So let's just do the product rule. I mean, we're going to have to do it either way. So first, derivative of second plus second derivative of first. We could try to clean that up if we wanted to. I'm just going to stick in the limit and see what happens, okay? So let's see, if I put this in there, and I'm basically going to get 1 minus 1, which is 0. If I stick in 1 here, I'm going to get that piece is 0, which wipes that out. And then this is back to thinking about our graph. As we approach 1 from the right, that's going to be 0. So we got 0 over 0, so dang it. Well, not dang it, but I'm going to have to use probably L'Hopital one more time, or I can at least. I know it's feasible to do so. So I'm going to say this is equal to the limit as x approaches 1 from the right-hand side. And what happens now if we take the derivative here?
1 over x squared on the top. But then it cancels
let's
off
see.
the other negative.
Negative 1 over x squared.
Just 1 over x squared.
So it should be normal because the minuses cancel out.
Where? Sorry. I'm
Well, because
tired.
well,
It's x to the negative 1. That's what you take the derivative of that.
Oh, it's just positive x. Yeah, you guys are right. So nice, thank you. This one on the bottom, let's see. I don't know. So this is going to be 1 over x, right? I bet there was a more clever, simplifiable way to do this, but I'm tired. So that's derivative 1 over x, right? And then this guy, am I going to have to do the product rule again? I think so.
You don't have to.
Oh, I'm either going to have to do the product rule or
You have 1
You
minus.
have 1. If you
You
distribute,
have
you
1
have
minus
1 minus 1
x.
x.
I should distribute first, right? So a little scratch work off to the side. This piece becomes x minus 1 over x, which is really just 1 minus 1 over x. And now for the derivative of that, we're going to get 0. And you guys just help me do that one on the top, right? It's
1
going to
over
be
x squared.
1 over x squared. And we got a plus in between here. So let's see if that one comes out any better. So now sticking in 1, well, it's just going to be 1 on top, right? 1 squared is 1, 1 over 1 is 1.
Over 2. Yay. Yay.
So that limits 1/2. Okay? Sweet. All right, let's do one more. So I had this one in mind. Limit as x approaches 2 from the right of 8 over x squared minus 4 minus x over x. Was that plus 2 I have over there? It's minus 2, I think. Okay. So notice, Gabe asked me the question before we began today. He said, do we have to use, prove or show that things are continuous, the functions we're dealing with are continuous in order to do things? Remember, that assumption was only necessary to pass a logarithm inside a limit. Did we do that at all in this last one? No. Are we going to need to do that on this one? Just look at it and tell me if you think we're going to need to use the logarithm technique. You're saying no, Brandon. Why?
I see a common denominator.
Because this is going to be another common denominator problem. Which ones are you going to probably, not only those, but which ones, what's the giveaway that you might want to use the logarithm technique where you are going to have to worry about continuity? Yeah, when you've got a power of
Something. X.
x especially, yeah. But it might be useful on other problems as well, but the power of x really gives away that the logarithm is going to bring that down. So that's pretty easy to identify. Now, if you're running into one where you can't get something to work after L'Hopitaling it several times, you might want to try logarithming it. That might be a good idea. Okay? All right. So this guy, if we plug two numbers like 2.001 in, what would happen? So we'd get 2 over...
Nothing.
Something is not.
Careful, you got to look at this one carefully. So that's like 2 pretty much. You can just stick 2 right here. If you put 2 on the bottom though, you get 0. But But you don't want to think about it like that. Remember, this is as you approach. The whole idea of limits is approaching instead of actually what happens exactly there. That's what calculus is all about. So we can think of it pretty much being like 2 on the top
Over something really, really, really small.
over something really, really, really small. Exactly, because it's going to be something close to 2 on the right-hand side. Subtract another 2 and you get the really small part, but 2 over something really, really small is quite large. Very big. Depends on how small this thing is, but remember, when we say approach, we mean actually go all the way, which means divide by something infinitely small, which means get infinitely large. Okay? So just reminding you. So that part is infinity, and we've got a minus. What happens here? If you take 2.0001 and you square it and you subtract 4, then you get like 4 point something minus, I don't know what this number is. But you're going to end up with, which is really small, and it's the same thing, right? So this is another indeterminate form of infinity minus infinity. That's not good to go, so Brandon told me I should use a common denominator and see if that pays any dividends. So let's see if it does. What's the common denominator of these guys?
X squared minus 4.
Where's the x minus 2?
Inside the x squared.
Duh, right? It's not duh for a lot of people, though. So careful, yeah? This already has that factor embedded in it. So what's the only thing I need to fix it up with for my common denominator?
X.
So this is done, right? This one needs the
X plus 3.
this part. So I'll just show it this time. Still got the minus, and I've got x squared plus 2x, right? And let's see what happens now. Now if we plug 2 in, we'll get the same kind of thing on the bottom. So we'll get pretty much 0 on the bottom, right? If we put 2 in on top, that's going to be 8 minus 4 plus 4.
You have to put parentheses.
Did I make a mistake?
You need to put parentheses.
Oh, I did make a mistake. What did I do, Katie?
You put parentheses. You didn't distribute the negative.
But there's a minus. Oh, man. That's like one of the worst mistakes a student or, God forbid, a teacher could ever make. And I didn't even make it on purpose here. Danger, right? Jeez. Okay. Nice. Okay, so if I plug that in now, I'm going to get 8 minus... That's what I was thinking was going to happen. Otherwise, we'd have had to say the limit does not exist. Or we'd have to think about, the size again. So, all right. So L'Hopital time. So this is equal to the limit as x approaches 2 from the right. Due to L'Hopital's rule.
Negative 2x over 2 over 2x.
That was easy. So now if we stick it in, we get 4 and negative 4 minus 2. That's a finite number, done. So there you go, there's another indeterminate form with infinity minus infinity. Remember, just make sure very much so that you can do that one with the definition of e and the logarithm in the previous video in your sleep. That's very important. See you next time.
But why would we want to do